Okay, what we're going to cover in this review slide is convective heat transfer, and just a tiny bit that we've covered with regards to how it applies to our analysis of conduction. Now, what we're going to utilize is Newton's law of cooling, which is given by the heat rate is equal to some proportionality constant times an area times a temperature differential. And how we're going to define these is by defining a solid substance given by the blue box here, and we're going to have a fluid flowing over it at a velocity u infinity and a temperature T infinity. And how we're defining these infinity terms is that this is the temperature and velocity that the free stream has beyond the influence of the solid substance. The solid substance will consider having a surface temperature of Ts, and the heat rate is going to be the heat that's moving from the solid surface into the fluid, and we're going to call this convective heat transfer. Now H we're going to recall as the convective coefficient. It has units of watts per meter squared per Kelvin, and it is a function of a number of variables. In this case, we can think of them as being fluid velocity, fluid properties, and the surface geometry. And again, when we discuss convective heat transfer in more detail, we will be looking at primarily how to calculate values for the convection coefficient. Now, we're going to introduce a term for convective thermal resistance, and this is going to allow us to be able to combine the convective heat transfer with conduction. And how we're going to define it is that the thermal resistance for convection is going to be equal to 1 over the product of the convection coefficient times the area of interest. And once we've written the thermal resistance in this manner, we can then rewrite Newton's law of cooling in essentially our electrical analogy, and this is going to allow us to combine it with Fourier's law. So what we're going to be able to essentially do now is look at energy being conducted through a solid, and then that energy can be transferred to a surrounding ambient environment via conduction. So to get you an idea of what we're looking at, we're going to have a composite wall made up of 3 different substances and 3 different widths, giving us 3 different thermal resistances, conductive thermal resistances. And on the left-hand side and the right-hand side of this composite wall, we can have a flowing fluid. On the left-hand side, we'll call it T infinity L, and we'll have a corresponding convection coefficient, and on the right hand side a similar situation. So you could think of this as flowing hot fluid on the left hand side and flowing cool fluid on the right hand side, and we're interested in what's going to be the rate of heat transfer between those 2 fluids. Now, what will essentially be usually unspecified are the actual surface temperatures, in this case TA and TC, and the interface temperatures TAB and TBC. Now the way we'll go about analyzing this problem will be using a thermal circuit where the endpoint temperatures, the motive force, are the ambient temperatures T infinity L and T infinity right. At the junctions between the various resistances, we'll have these intermediate temperatures, which are essentially unknown until we go ahead and solve for the total heat transfer rate. Then we can solve for them individually. And we have RA, RB, and RC, which are conductive thermal resistances. And then on the outsides, we're considering the convection thermal resistance given as 1 over HA. Now we can put this all together, and in this case I'm writing it as a heat flux, so we're going to multiply through by the area of interest, giving us a heat flux, and in this case we are essentially utilizing the temperature differential of the ambience on the left and the right hand side divided by the total sum of all the thermal resistances, both conduction and convection thermal resistances, to give us the total heat flux. And just to, again, take a look at the direction of heat transfer. For this particular case, a positive value would imply that the flow of heat is from the right-hand side to the left-hand side. And again, you want to make sure that you, when you calculate your heat transfer, that you indicate a proper direction. All right, and this ends this particular review of convective heat transfer.